All right, so before we get into all the details about what this symmetry-protected topological order is, I want to try and motivate you why you might care about these things from a quantum information perspective. So the idea is this starts back with the old question of how do we design devices that are robust to noise and can maintain their coherence. So what kind of material should we build these devices out of, and what kind of principles should we use to select them? And promising direction in recent years, and the perspective I'll be taking for this talk, is that these topological phases are great candidates for the type of design of these quantum information systems. So they're fascinating in their own right, but they also have some natural robustness and some natural order, which makes them good for quantum information tasks. And so the key idea and the key understanding is that the order that you have in some of these systems, in the collective degrees of freedom of many interacting spins, gives rise to a robustness that you can make use of. And a classic example, and a classical example that I'm sure everyone's familiar with, is this 2D Ising ferromagnet. So here you have some 2D system of classical spins that are interacting, and you can use this for a self-correcting classical memory. So the idea is that you encode your classical information in the degenerate ground space, which is consisting of all spins up or all spins down. And then provided you're below some critical temperature, the system will exhibit some ferromagnetic order, which protects your information for a long time. So if you go in and try and flip a spin, there's going to be some energy cost associated with this, and this dominates any possible entropic advantage. And so you're going to have a long lifetime of your classical information. And then a more quantum example of this phenomenon is Kitaev's toric code. So this is a 2D lattice system, and you can think about this as identifying the opposite boundary, so we're in a toroidal surface. And then this is a quantum error correcting code at zero temperature. So you encode information in the degenerate ground space again, and it's associated with these non-local degrees of freedom. And so any local noise that acts on the system is not going to damage your non-locally protected information. And key here is that this toric code is only stable at zero temperature. So it has this topological order, and that's only stable at zero temperature. We know of some examples of systems that exhibit stable topological order at non-zero temperature, such as the 4D toric code. And then we're trying to, this is an important question, trying to move towards more physically realistic situations and systems, such as perhaps in 3D, where there's been a lot of interesting proposals and candidates, such as Haas cubic code, or McNickey's welded code, or even Brell's code. These are interesting proposals, but so far the question is still open as to can we have this topological order or a self-correcting quantum memory in 3 dimensions or less. Right, so this is an important problem, and this is kind of the idea behind this talk. So what we're really going to be talking about here is a kind of more subtle class of systems called symmetry-protected topologically ordered systems, or just SPTs for short. And these are systems that possess some subtle order that's only present in the presence of some symmetry. So before we had these toric codes, there was no symmetry there, but it had a natural order. Here we require a symmetry to maintain this order. And these are zero temperature, these are ground state properties of a system, this order, this SPT order. And we want to know, are they stable, is this order stable at non-zero temperature? And so just like the previous talks, we're going to be talking about Gibbs ensembles. And so the plan for the talk, first we're going to introduce what are topological phases of matter, what this means at the level of the Hamiltonian and the level of the state, and then what are these SPT orders. And then we're going to go on and talk about this first result, which is the thermal instability of a large class of SPT systems. So there's a broad class of systems called the group cohomology models, and we'll mention them. And these are the class of systems that we're going to use to model this, and we're going to say that these systems are not thermally stable. So the SPT order vanishes at non-zero temperature. And then as a second result, we're going to talk about the existence of some thermally stable SPT systems. And this will be the 3D cluster model that underpins this topological formulation of measurement-based quantum computation. but we'll talk about this in a minute. All right, so what are topological phases of matter? So we're going to be considering systems of spins on a lattice. It's going to be finite at first, and then we're going to take the thermodynamic limit in the end. So we're going to take the limit of infinite system size. And then these are governed by some local Hamiltonian. So it's a sum of local terms. Each term acts on a bounded region, a bounded number of spins. And then we're going to be interested in the class of models that are gapped. So these have a finite gap from the ground space to the next excited space, and this gap persists in the limit of infinite system size. And this is really a niceness assumption. You could consider gapless systems as well, where the gap closes. But these are, gap systems are hard enough to understand already. And gapless, they're interesting in their own right, but they're even more complicated in some sense. Right, and so what is topological order? Well, we say the defining property of topological order is that the ground space properties are robust to any small perturbation that's local. So if you can add some local terms and they're of sufficiently small strength, then this gap's going to remain open, and your ground space properties are going to be maintained. And so this really lends itself to the idea of a quantum code. So here we can think of these systems as quantum codes because we can encode our quantum information into the degenerate ground space. So you can think of these 4 states as, say, the state space of 2 qubits. And examples that we've already been hearing about are these toric codes. That's the easiest example, and it's a very rich example. And then we've also been hearing about these color codes earlier in the week from Hector. And right, so the idea is also, these degenerate ground spaces, the logical information is encoded in these non-local degrees of freedom. So because these systems have a robustness to local noise, then the ground states are going to be also robust to this local noise. And that's why we can really think about them as good codes. Any noise that acts local on the system, so it only has access to some finite amount of, some bounded number of spins, it's not going to compromise the information that's protected in these kind of topological degrees of freedom. And a consequence of this is that you'll often see ground space degeneracies that are associated with the topology of the surface or the topology of the manifold that these systems are defined on. So in the toric code, and you define this on some surface, you're going to see that the degeneracy goes as 2 to the 2g, where g is the genus of the surface, the number of handles. Right. So I've talked about these ground states a lot, but and what it means to have topological order at the level of the Hamiltonian. But you can come up with a formulation in terms of ground spaces, in terms of ground states as well. So the idea of a quantum phase is it's a collection of quantum states that are equivalent to each other up to local unitaries. So a phase is an equivalence class of states, and 2 states are equivalent if they can be related by a constant depth unitary circuit. So this constant depth unitary circuit is comprised of these local gates here, the depth of the circuit is going to be constant in the size of the system. And this gives rise to the idea of the trivial phase. So this is all states that can be reached from a product state by a circuit of constant depth. And then there's these topologically ordered states. So they're ones not equivalent to the product state. You can't disentangle these states using only a constant depth circuit. So systems that we study often have symmetries. So symmetry is a very natural thing to consider in physics. And one such symmetry you might think of is this Ising type symmetry. So you flip all the spins, and if the system is invariant under this spin flip, then it's a symmetry. And these symmetries, as we heard about in Frank's talk, you might think of them as constraining the theory, but it actually gives rise to much richer physics. So you could take this is supposed to represent some phase diagram, and each of these colored regions is supposed to be an equivalence class of states, so it's one of the phases. And then if you consider imposing some symmetry on the system, so you're only allowed to move between states that obey some symmetry constraint, you can consider perhaps this is the trivial phase here, this blue region. So it's all states that can be reached by a constant depth circuit from a product state. And then if you require that these circuit respect some symmetry, then it turns out that this trivial phase splits up into many interesting phases. So you might still have this trivial region down here, but then these guys can't be reached by a constant depth circuit where the gates are required to respect some symmetry. Right, so an example of this, and it's probably the simplest example, is the 1D cluster state. So this is a state on a chain. You have this Hamiltonian here, which is a stabilizer Hamiltonian. It's all the nice properties that you would want. All these terms are commuting, and you have one term for each site. And the ground state of this is the cluster state. And this is a short-range entangled state. You can prepare this by initializing all of your qubits in the plus state, and then doing controlled Zs between neighboring spins. And so this is a low-depth circuit, and this state and this model belong to the trivial phase. However, this system has many symmetries, one of which is this Z2 cross Z2 symmetry here. So you can take one of the generators as flipping all the spins on odd sites, and then this other symmetry, which flips all the spins on even sites, and you can check that this commutes with the Hamiltonian. So this is a symmetry of the system and of the ground state. And it turns out that if you ask the question, can I prepare the cluster state from a product state using a circuit comprised of symmetric gates, can this be done in constant depth? Turns out the answer is no. You need a circuit depth that scales as the size of the system. And so this is really the definition of SPT order. These are states with some symmetry, and you can't connect them to a product state using a circuit comprised of symmetric gates unless the symmetry is broken. So they're trivial without the symmetry, but in the presence of a symmetry, they're non-trivial. And a rich class of models which you can use to generalize this cluster example is the so-called group cohomology models. And so I'm not really going to go into detail as to how to construct these, but it's a nice construction. But the important idea is that these are models on some lattice, and they're some of commuting terms. They're commuting projectors. And they have this thing called an onsite symmetry. So this global onsite symmetry, where global onsite just means that the symmetry acts on the entire system, so it affects all of the spins. And it's also generated by this local action that acts on a single site. And these models you can use to write down lots of non-trivial SPT models in all sorts of dimensions using all sorts of symmetry groups. And why would we care about these things? Well, it turns out in recent years there's been a lot of work that connects these states to useful applications. So one of the main ones is this measurement-based quantum computation. So here the computation proceeds via single qubit measurements on some highly entangled resource state. And this is a universal scheme provided your resource state is the right kind. And so there's been a lot of results that say SPT ordered states give the right kind of structure for measurement-based quantum computation. That is, you can use these states for universal resources. And moreover, there's a lot of results that say these are robust resources. So you can perturb the state by some symmetry respecting perturbation, and then the state will remain universal. And you don't even have to know what the state is exactly. You don't have to have a precise description. As long as it's within the phase, it remains universal. And these are results from, say, Raussendorf and David Stephen and Dominic Else and company. There's many more, but I couldn't list them all. And then on the other side, SPT-ordered states have shown applications in quantum codes, in topological codes. So here's the idea of a gapped boundary. So you might want to define your code on some toroidal situation. This might be too hard to achieve in a lab, and you want to write it down in some planar surface. And you ask, what kind of boundaries can I have that leave the system gapped, where I can perhaps move excitations and condense them in the boundary? And it turns out that SPT-ordered states give rise to, you can use them to construct gap boundaries, and you can use them to classify these types of gap boundaries, what kind of boundaries you can have on a code. And then moreover, you can use these SPT-ordered states to construct fault-tolerant logical gates. So you want gates that are locality preserving, so they don't map errors to too many more errors. The errors are kind of keep local. Then you can use these SPT-ordered states to define these gates. So they're pretty interesting states. And the question is, What about all of these at non-zero temperature? Can we have thermal resources for measurement-based quantum computation? Can we have thermally stable gap boundaries? These are all questions that might come from answering this question of what happens to SPT order at non-zero temperature. And so here's the kind of context of this talk. So far we've seen without a symmetry, there's these topologically ordered states. At zero temperature is the 2D toric code. And then at non-zero temperature, you have this 4D toric code. And then in the presence of symmetry, you can actually get these topologically ordered states in 1D. So previously, to get without a symmetry, you need 2 dimensions or more to achieve topological order. But if you have a symmetry, you can achieve this in 1D. And then cluster state is the example you should keep in mind there. And then this non-zero temperature question has kind of not been answered so far. And of course, in a realistic situation, we don't have systems at zero temperature. We don't have the exact ground state. So I think that this question is kind of important for practical implications. Right. And so this is just the problem stated, as I just mentioned. Do any of the ground state properties of a SPT-ordered system survive at non-zero temperature? So we already know that they have this robustness to perturbations, but can we turn up temperature and still have this ordered phase here? And this has these implications that I mentioned before. And so what do we show? We rule out a large class of models from having thermal SPT order, but that we have to suitably define, as I will in a minute. But then to show that this formalism is kind of useful, we also show that there's this model which does have thermal SPT ordered. So there exists thermally stable models in 3 dimensions, and maybe even 2 dimensions. And then I'll discuss some of the computational aspects of this ordering if I have time. Okay, so let's ask this question: what is SPT order at non-zero temperature? And this work is really inspired by Hastings' work on the question on topological order at non-zero temperature. So the starting point is this Hamiltonian that has some symmetry that's unbroken. And we want to ask the question, what is the order in this Gibbs state? So this is the Gibbs state at inverse temperature beta. And how do we define what is the non-trivial order? And so we're going to use circuit depth to define the non-triviality. And to replace the notion of triviality, so the product state was the trivial example, we go to this classical ensemble. And this is just the ensemble of some Hamiltonian that's diagonal in some local basis. And you should just think of a classical Hamiltonian as this paramagnetic example here. It's non-interacting. Right, so here's the definition. The idea is that we want to say how non-trivial is the circuit depth required to prepare the SPT ensemble from a classical ensemble. And so we have these 2 parameters here, R and epsilon. R you should think of as the depth of the circuit required, and epsilon is the error. So here we start with this classical ensemble, and then you're allowed to do a symmetric unitary of depth D, of depth R, sorry, on this enlarged system. So this classical Hamiltonian is on some enlarged system. And then you have to trace out the additional degrees of freedom and see if it's a good approximation to your SPT ensemble. So that's the question. And you would say that a state is trivial if it's R epsilon trivial for small r and small epsilon. And so the first result is this instability of SPT models protected by a global onsite symmetry. So for any non-zero temperature, and you have one of these models protected by a global onsite symmetry, they're trivial. And that is they're R epsilon trivial for R, which is basically logarithmic depth. You can bring this exponent down here if you like. And also epsilon is inverse polynomial in the system size. And this works for any dimension D. And we prove this for this class of models described by group cohomology that I mentioned before. So let me just remind you, these are these lattice models that are comprised of these commuting projectors. And so how do we prove this? The first technical tool is really this approximation by an imperfect Hamiltonian that we first saw in Hastings' work and then later in Siva and Yoshida. And so the idea is you take this Hamiltonian, sum of local terms, and then you remove terms from the Hamiltonian with some probability, P. And this probability depends on the temperature. And then you get this imperfect Hamiltonian over here, which has these removed terms. So that's what's illustrated here. You have some lattice, and then you kind of remove these Hamiltonian terms here with some probability. And this probability, you'll see that at 0 temperature, it goes to 0, and then at infinite temperature, it goes to 1. So this kind of matches up because at an infinite temperature, your Hamiltonian is just going to be a constant matrix, and so the Gibbs state is going to be some maximally mixed state. And so the idea is that once you have this imperfect Hamiltonian with the removed terms, the ground space of this Hamiltonian approximates the Gibbs state of the SPT ensemble polynomially well. So we only really have to think about the ground space of this imperfect Hamiltonian now. And now the goal is to try and disentangle this Hamiltonian with a low-depth circuit to show that it's trivial. So here, we can construct these local disentanglers, and the idea is that around each of these missing terms here, is what these red dots are supposed to illustrate, you can construct a local disentangler. So here, I don't know if you can see these blue regions, that is, you can disentangle all of the terms that are in a small neighborhood of this missing term. And then you can continue going, and you can continue disentangling. And then if you take this kind of grid, you can partition your lattice up into this grid where each of the side lengths is square root of a log. Then you can guarantee the existence of a missing term within each region, each log-sized region with high probability. So then you can see that if you continue applying this circuit, you're going to need to disentangle log L spins within each region, and each gate is, of course, bounded by this log-sized edge. And so the circuit depth was, as claimed before, it's logarithm to some exponent. And I should mention that the logarithm is kind of essential here because we're assessing the error in trace norm, and so you can't really expect to have a constant circuit depth. Log is kind of the best you can do. And so what this gives is it gives a low-depth preparation of the SPT ensemble. And that shows that these models are trivial. And so what are these models? How broad is this result? Well, the group cohomology models completely classify SPT phases in dimensions 1 and 2, provided you have this global on-site symmetry. And so these models, they're stable at 0 temperature, but once you turn on the temperature, then they're non-zero. They're trivial, sorry. And what does this mean in terms of the computational structures? Well, some of the results that heavily depend on this SPT order to use these states as resources for measurement-based quantum computation seem to be unstable. But that's not too much of a constraining result, because one way of getting around this would be, for example, to prevent your system from thermalizing. And then the question now is, how do we get around this result? How do we look beyond group cohomology? And then this leads us to the second part of the talk, the existence of thermally stable SPT order. And so we're going to switch gears a bit here, and we're going to go back and look at this model first defined by Raussendorf-Bravyi-Harrington, and show that it belongs to a non-trivial SPT phase at non-zero temperature, provided it's below some critical temperature. So what is this model? This is a very interesting model. It's the underpinning of this topological formulation of measurement-based quantum computation. And it's really, it's the kind of substrate of this computation. So you can think about, this is a 3D lattice, and you can think about one of the directions as being simulated time, and you do these measurements to kind of induce movements of these punctures in a 2D toric code. That's the idea there. And this is one of the highest threshold schemes currently. It sits at about 1%. And this is kind of pretty magical, and we want to understand what's really underpinning this order. So additionally, some of the computation can work thermally up to some critical temperature. So one of the primitives in measurement-based quantum computation would be to generate Bell pairs between distant regions that you can use for gate teleportation. And you can do that with this state even when it's thermal. However, it works up to some critical temperature, but then there's no thermodynamic phase transition in the model. The model, it just behaves as though it's completely uncoupled. So what is really underpinning this high threshold and this thermal stability. That's what we want to understand, and we're going to explore it in the context of this SPT phases. So more precisely, what is this model? You start with a cubic lattice in 3 dimensions as such, and you put qubits on the faces and qubits on the edges. And so I've just labeled these by different colors. And then the Hamiltonian is, again, a stabilizer Hamiltonian. It's given by this sum of these k terms, and these k terms are 5-body terms. You have one for each qubit. It's an x with the z on the surrounding qubits. And these terms all commute, and you have this unique ground state, which is the cluster state. It's the +1 eigenstate of all these terms. And then additionally, you, just like in the 1D case, you have this efficient preparation. You initialize all the qubits in the plus state again, and then you do Control Z between neighboring qubits. And this gives a preparation of the ground state. And so this state is trivial in the absence of symmetry in terms of topological order, but this model enjoys several symmetries. And we're not going to look at the onsite case because, as we mentioned before, this is already ruled out. But we can think about more general symmetries, such as this so-called one-form symmetry. And so the idea here is that you can have a symmetry operator for every 2-dimensional surface. And an elementary symmetry operator is given by this guy here. So it just acts on the 6 qubits surrounding a cube, and acts as an X operator on these guys. And these type of operators are symmetries of the Hamiltonian. You can verify. Indeed, this operator is actually a product of these cluster terms around the 6 faces. And it's called a Z2 cross Z2 symmetry because you have one copy of each of these symmetries for each sublattice. So you have one for the blue guys that I haven't written here, and one for the green guys. And these operators, they naturally occur as the check operators in these measurement-based schemes. So they're kind of physically or informationally motivated. And so this is the second result, which is that there exists some critical temperature such that below this temperature, the thermal state of the RBH model is SPT ordered under this one-form symmetry. And there's 2 ways of going about this. One is explicitly constructing order parameters that have low value in the trivial phase and then show that they take on a high value for the Gibbs state of the cluster model. And then secondly is this idea of gauging. So we heard from Frank, he gave a talk about gauging, and it turns out here that you can use gauging to assess the non-triviality of SPT order. And I'll probably mention this toward the end if I get time. And these 2 proofs actually have some kind of operational interpretation. So the order parameters that we use are really motivated from this paper by Raussendorf-Bravyi-Harrington, where they consider this scheme of trying to generate entanglement between distant regions. And you can lift that to this operator level and then use that as an order parameter. And then secondly, in terms of gauging, you can view this as the construction of some domain wall in a 4D toric code. But I'll mention that a bit more later on. So what are these order parameters? They're non-traditional in the sense that they're macroscopic. So these order parameters are sheet-like, they're membrane-like. So they consist of X's on this 2-dimensional surface. And I should mention that I'm thinking of this as a 3 torus. So I have the front and back faces identified and the top and bottom identified, and then we just take this third direction off arbitrarily large. And so these operators look like symmetry operators in the bulk, but then they have some kind of dressing on the boundary. So this guy is X's, and then it has Z's on the boundary. And they're also non-traditional order parameters in the sense that we allow for some error correction. We don't just take the raw expectation value of these operators. We allow for some error correction before we take the expectation value. And they're constructed such that a trivial state will have low expectation value of these guys. So if you have R epsilon trivial state, where R is less than the lattice size, and also epsilon is small, then the expectation value of these membrane operators, even in the presence of error correction, is going to be small. And you should really think about this as this construction is that it looks like a bulk symmetry operator, a symmetry operator in the bulk of this membrane, And so you can kind of ignore that. And then on the boundary, you have these strings of x's and then these strings of z's, and they look like toric code strings. And so you should think about this as how do I get a high expectation value of this XX and ZZ, which is the correlation amongst the entangled pair, and you can't do that with product states, right? This is going to be bounded by 1. And then in terms of the RBH model, how do we show that this takes on a high expectation value of these membranes? Well, first we need to do some error correction. So this can be viewed as symmetrizing. We want to make sure all of these one-form symmetry operators are +1 in the Gibbs ensemble. And so the thermal state of this RBH model consists of strings of violated cluster terms. So your stabilizer terms are violated along these kind of red squiggles, and they're string-like. But then if you measure these one-form operators, you get information about the boundaries of these strings. And then the idea is you want to have some procedure of closing up these strings such that the one-form operators are now +1. And then you also want to do it such that you don't introduce any homologically non-trivial excitations, or you want to suppress them as much as you can. And so we don't want to have any excitation that wraps from the top of the lattice down to the bottom. And if the error correction succeeds, if you don't have any of these homologically non-trivial excitations, then all of these closed loops of excitations are going to commute with your membrane operator, and so we can guarantee that each of these membrane operators will take on a +1 expectation value. And importantly, this error correction procedure only works below some critical temperature. And this is due to the low temperature phase having this string tension where strings of large length are exponentially suppressed. And so operationally, as I mentioned, what do these autoparameters really mean? Well, they quantify the ability to distill maximally entangled pairs between different distant regions, where we think of these pairs being encoded in some toric code. So these X's and Z's are the logical operators of a toric code in some slice of the lattice. And we can do this using only single qubit measurements in the bulk. And this is really the content of the original RBH paper. And then you might also wonder, this definition of SPT order seems to be protocol dependent because it depends on the choice of decoder. But actually this is no problem because you can always use the optimal decoder. There's a provably optimal decoder. In this case, it's maximum likelihood decoding. And so this gives an upper bound on the critical temperature. And then, so in the last kind of minutes, I'm just going to briefly talk about this gauging procedure. So the idea here is that we want to construct some domain wall in the 4D toric code. So what a domain wall is it exchanges these loop-like excitations. So in the 4D toric code, you have your excitations form these loop-like objects, E and M type. So E corresponds to loops of violated X terms, and M's correspond to loops of violated Z terms. And you want to construct a domain wall which exchanges these two. And so what you do is you can construct this 4D system. You take such as here. This is a 3D picture, but anyway, just imagine it's 4D. So you take this 4D bulk and you put a trivial model there everywhere. So you put trivial paramagnetic model in the bulk, and then on the boundary, which is a three-dimensional boundary, you put the RBH model. And then this whole system is Z2 cross Z2 one-form symmetric. And then you can apply some generalized gauging procedure. So Frank considered gauging these global onsite symmetries, but you can do a similar procedure here where you gauge these more local one-form symmetries. And what you end up getting is that this trivial bulk gauges to a 4D toric code. And then this boundary region, it gauges to something that's it's like 4D toric code, but it's addressed in some way. And then if you unfold this boundary, so you kind of pull some of the toric code over this other side, you can consider it as a domain wall between two regions of 4D toric code. And that you can check that this domain wall exchanges the E loops and the M loops, right? And so this is actually a sign of non-trivial SPT order because you can't prepare a domain wall with a constant depth unitary circuit, a non-trivial domain wall anyway. And then the fact that this 4D toric code, you have these exchange statistics between loops, and they survive even at non-zero temperature. This is also a sign that this domain wall is non-trivial at non-zero temperature, and therefore the SPT order is non-trivial at non-zero temperature. All right. And so with this, I'd like to conclude. What did we talk about? We talked about thermal fragility of SPT models that are protected by global onsite symmetries. And then we showed this existence of the SPT order in the 3D cluster scheme. And this is really helping us to try and understand what are the right properties that make a good resource for measurement-based quantum computation. And then we briefly discuss some of these computational aspects. And really here, we want to make steps toward understanding what is possible and what kind of schemes we should develop. So we can, this RBH scheme, well, this topological formulation of measurement-based quantum computation is already high threshold, but maybe we can be greedy and try and ask for more, ask for higher thresholds and lower overheads. And so what we do is we want to keep writing down these toy models. And then there's some further questions. So this is an important one that I think is already being pursued. But so what is the connection between SPT order and measurement-based quantum computation? We have lots of examples of connections, and there's a nice correspondence. But really pinning down this connection, and moreover pinning it down at non-zero temperature. And this is analogous to the question of thermal topological order and its correspondence to the existence of self-correcting quantum memories. And then we've already seen that there's this domain wall in the 4D toric code, and it seems like in 3 dimensions and higher, there's all sorts of possibilities, and understanding these and their thermal stability is an interesting question. And then also developing principles to understand the single shot error correction that you see in the 3D gauge color code, and trying to develop more models that exhibit such behaviors. And then, of course, more models have maybe even symmetry-enriched topological phases at non-zero temperature, and also maybe models that exhibit nicer transversality properties. Because the RBH model is really built upon this surface code architecture. And with that, I'd like to thank you.
Questions?
I would like to ask if you could add a bit more insight to why can you apply this disentangling procedure only in the presence of one missing term. You had this logarithmic grid.
Right. Yeah, so the idea is that if you didn't have this missing term, then any kind of local symmetric gate that you're going to apply is only just going to entangle these two terms in some way. You really need to have the absence of a term such that you can map it to a trivial, you can map each term to a trivial term without affecting the remaining terms.
Thank you.
So I have 2 questions. My first question is that, am I correct that the proof of thermal stability relies on the fact that the excitations are, well, they have this string tension?
Could you just repeat the first part again? Sorry.
So is it crucial in your proof of thermal stability that your excitations have string tension?
Yes.
And my second question, that is this why you don't think that one form SPTs are probably not thermally stable in 2D?
Yeah, so that's part of the reason in 2D. You tend to not have this string tension. The excitations are deconfined. But yeah, there may still be some hope in 2D, I would say.
Okay, thanks.
Okay, if there's no more questions, let's thank the speakers again.